Alright, so we're going to start a new walkthrough series. This is the NCERT Chapter 1 on real numbers. Now, if you follow along in your textbook, you should have done the previous reading where we discussed the NCERT book. Your book should have discussed the beginnings of real numbers and rational and irrational numbers. We're going to do a quick review as that's what we start in this chapter. So rational. So to start off, we need to define rational and irrational numbers. So rational can be expressed in the form a over b, where a and b are integers. If you see me using this symbol, this just means in the set of. Right, but this is just r. You can just write r integers. Don't use this symbol because I'm not completely sure if NCERT uses this symbol. We might in the future. So irrational numbers are the opposite. Irrational cannot be written in the form a over b, right? And we switch right here. Alright, so cannot be written in the form a over b, or a over b. Right, can't be written in the form a over b or a, b in integers. And now we should do examples of rational and irrational numbers so you can understand. So this is like negative 2, 3, 4.17, negative 12 over 19, negatives, like all these are rational because they can be written in the form a over b. And also another example of rationals is 0.6 repeating, 0.75 repeating, because these repeating decimals can be written in the form a over b. And irrationals are all like radicals, so cube root of 10, square root of 15. Any square root of a non-perfect square is irrational, or cube root of any non-perfect cube. So if you have like the nth root of a number, and this number is not a perfect like nth power, then that's going to be irrational. Right, so like cube root, square root of 9 would actually be rational. Right, because square root of 9 is 3, and 3 is rational. Right, so we can write another example, 10. I can't have the square root of a negative number that becomes non-real. That number is not real. Square root of 1 plus, or square root of 1 plus 2. And then also numbers like pi. Pi is irrational because pi is not repeating. It's an infinite decimal, right? And numbers that are multiplied by pi, 5 pi, 10 pi, minus square root of 2, etc. So these are rational and irrational examples. Now, most of your work, a lot of your work in this chapter is just focused around rational numbers. That's what the main focus of today's video will be. So rational numbers, you need to know that rational numbers, we're going to be dealing with integers, right? When we deal with integers specifically, we're going to be looking at positive integers. And we're going to be looking at a theorem called the fundamental theorem of arithmetic, or FTA. Right? The fundamental theorem of arithmetic states that any positive integer n can be written as a product of primes, can be broken down to a product of primes. So it can be written as p1 to the e1 times p2 to the e2, and all the way until pk to ek for any value of k that's greater than these two. And basically what this is prime factorization. So you should probably, this is like prior knowledge, but I'll go over it again. When we break down an integer into a product of primes, that is prime factorization, which is what we have. Okay, which is what we have over here. And an example of this would be, for example, if I take 27. 27 is 9 times 3. 3 is prime, right? And 9 is 3 squared. So, and when we write prime factorization, we want to keep the exponent. We don't want to write like, we don't want to write like n equals p1 times p1 times p1. Instead, we want to write this is p1 cubed, right? In this case, it's 3 times 3 times 3, right? Which is what? 3 cubed. So that's the prime factorization of 27. And you can do this for any positive integer. If the integer is prime, you can still write like, no, it's not prime. 17 is 1 times 17. Like, that's the prime factorization of 17. Although it's kind of useless for primes because we use primes as the building blocks of larger numbers. And using primes, breaking down primes is, you can't break down a prime because it's just one itself. Right, so when you have larger problems, you can use prime factorization to find the building blocks of that number. So now we have the prime factorization, all this knowledge, we can apply it to a problem. So I think NCERT gave you like 4 to the n. We modified it a bit. If you were able to do that, this is pretty easy then. But I've linked some harder problems in the description below, so check those out. So consider numbers 14 to the nth power, where n is a natural number. Check whether there's any value of n for which 14 to the n ends with a digit 0. So, where n is a natural number, this basically means anything, any positive, like non-negative integer, natural number. Right, another way you could have figured this out is if 14 to the n ends in the digit 0, then n cannot be less than 0, right? Because if n's less than 0, then if n's less than 0, then it's going to be a fraction, right? Fractional number, right? But if n is, let's say, 2 or 3, it's going to be in the double digits. So basically n is greater than 1. We have 14 to the n ends in the digit 0. Whenever you have a problem where there's an integer which is kind of like 14 is kind of large if you want to find like powers of 14. Like not many people can do 14 cubed in their head. 14 squared we know is 196. Right? If you didn't know that, like it's irrelevant to the problem, but you should find the prime factorization of larger numbers. So 14 is 2 times 7. Right? 14 is 2 times 7. And we want to check whether there's any value of n for which 14 to the n ends with the digit 0. So our number is 14 to the n, which is 2 times 7 to the n, which is 2 to the n times 7 to the n. So this is our prime factorization of 14 to the n. Now check if there's any value for n in which 14 to the n ends with 0. Well, if a number ends with 0, if you look at the characteristics of a number that ends in the digit 0, like 10, you can see that all of them are multiples of 10, right? Every single one of these is a multiple of 10. And if it's a multiple of 10, that means in its prime factorization, it has to have a 2 and a 5, right? So like 90 is 9 times 10. 9 is 3 squared. And 10 is always going to be 2 times 5. Right? The prime factorization of 10 is 2 times 5. So that means we have to have a 2 and a 5 in this prime factorization for 14 to the n and with a digit 0. If we take a look, we have a 2, but we don't have a 5. So the answer is just no. since we don't have a 5 in this prime factorization. Our answer is no. If you didn't really resonate with the 2 times 5 method, if you just look at 14, pay attention to the units digit, right? There's another like trick if you ever get stumped and you don't have to check for the, you have to show any work related to the method. 14 has a units digit of 4, right? So when I multiply 14 times 14 times 14, the units digit is just going to be 4 times 4 times 4, and the units digit of that. 4 cubed is 64, so the units digit of this multiplication is 4. And you'll notice that as you keep multiplying, like, there's a pattern for the units digit. So, for example, 4 to the 1 is 4, obviously. 4 squared is 16, so the units digit is 6, remember. And remember, units digit is just the last digit, right? Ends with the digit 0, meaning units digit. Right, you know we have units, tens, hundreds, or some people call it ones digit, right? Ones. So, and then 4 cubed has units digit of 4, and then 4 to the 4, well, what's 4 times 4? 16, so units digit of 6. And units digits cycle, and any number, if you have n to the k, the units digit of n to the k will cycle in some sort of way. Here, in this case, it's 4, 6, and then repeat. So, if the only possible units digit for 14 to the n is 4 and 6, then it can't end with the digit 0, and the answer is no. So that's another way of figuring that out. So now that we have prime factorization and the fundamental theorem of arithmetic, we can focus on GCF or HCF and LCM. NCERT likes to call it HCF, which is highest common factor. And then LCM is obviously least common multiple. Now, if you're going to study from outside sources, which you might not want to because NCERT does not use any other term, HCF is highest common factor. In other books, you might find it be GCD or GCD or GCF. That's usually in other countries as well, but NCERT does not use highest common factor or HCF. So HCF and LCM, how do we figure these out using prime factorization? So I want to do a general thing first. If you have HCF of m and n, right, of 2 integers, positive integers, then the method to find the HCF is you find the prime factorization of m and n, right? Prime factorization of m and n. And for the HCF, you look at the common prime factors. Look at the common prime factors in this. And every time you have a common prime factor, you look at the exponent that's less. So if I have like 2 to the 7 times, then there's more things here, and then I have times 2 to the 4, right? I look at these common prime factors, and I list every single common. So if I have a 3 here, then I have a 3 cubed here, and then I have a bunch of other different prime ones. We only care about the common prime ones, and then our HCF is just going to be, we look at the one with the smaller exponent, right? In this case, 2 to the 7, 2 to the 4. 2 to the 4 is a smaller one. In this case, 3 to the 1 is small. That's just an example. And you do this for each of these common factors. So if I had a 4 to the 4 squared and then 4 here, then I'd take the 4 and then add it to the multiplication. And when you multiply all these, you get the HCF. Now, assuming all these other prime factors are different, the HCF would just be 2 to the 4 times 3 to the 1, 3. That's your HCF. LCM is a bit different. For LCM, you again find the prime factorization of m and n. This time look at the common prime factors, and you see which one is greater. So you're at 2 to the 4, and then 3 to the 1 is right here. 3 cubed. You look at the greater one this time. And there's different prime factors. In the LCM, so here we look at common, and then we look at larger exponent. And we take the entire thing, so the larger one here is 2 to the 7, and the 2 to 4 we just don't care about anymore. Then 3 cubed, we put the 3 cubed here, we don't care about this anymore. And whatever prime factors are different, we have to multiply them. Alright, so this is P1, this is P2, this is P3 right here. So we have to multiply P1 times P2 times P3, assuming P1, P2, or P3 does not show up in N. So if this is like, this is D1, D2, D3, and these are all different, then this is D1 times D2 times D3. You keep doing this and you multiply all of them and you get the LCM. That's the LCM and HCF. Then before we go on to more examples, it's important to note that there's an important theorem you need to know, which is if you have positive integers m and n, then mn equals LCM of m and n times the HCF of m and n. This is important because if you have a problem where you have find the LCM and the HCF of the same pair of integers, then you can just use this theorem to multiply the integers and just find one of these. Usually HCF is quicker and easier to find. And then just divide mn over LCM, or mn over HCF to find the LCM. So let's do some examples. We'll do Alright. So pause the video and try these out. As with any example problems we went over, pause the video and try these out. Alright, so assuming you've tried it out, pause the video, so we're going to get into the solution. 12 and 16, LCM. We find the prime factorization. 12 is 2 squared times 3, 16 is 2 to the 4. LCM, I'm looking for the greater exponent. So I see a common prime factor of 2. I look at the greater one. So the LCM m and n is the greater one, 2 to the 4. We don't care about this anymore. Right? We don't care about this because we already used it. And now whatever's left, there's no other 3 here. So we just add the 3 on, multiply it. And this is 2 to the 4 is 16 times 3 is 48. That's the first one. Next one, 20 and 80. 20 is 2 squared times 5. 80 is 2 cubed times 5. So in the HCF, we don't care about anything that isn't common, right? So if we have 2 squared times 3, and 2 squared and then 2 cubed, we look at the one that's smaller, right? So then we have 2 squared is in the HCF. 20 and 80 is 2 squared. And then so we don't care about the 2's anymore. And I see this 5, but I see that the exponents are the same. When you're looking for the highest common factor, you want to see what's the greatest one that goes into both of them, right? And if you didn't know that the rule about the 5 being the equal exponent and you just ignored it, then you would probably get a wrong answer of 4, but you can figure out that 20 times 4 is 80. So obviously we need a 5, but whenever you have equal exponents, you have to multiply them, right? So if I have 2 to the 1 and 2 to the 1 down here, I have to just multiply it, right? Just put the original 2 to the 1. Now, and this is 4 times 5, which is 20. Cool. So that's LCM and HCF example right there. Now, if you ever have a problem, and I mentioned this above, and I'm gonna give you guys an example. If you have a problem which says like LCM of 2080 and HCF of 2080, I can go ahead and say, okay, 20 times 80 is 2 times 8 is 16. I pop 2 zeros on there. And then HCF is easier to figure out. You do this, you get HCF is 20. So that means we know that 20 times 80 equals the LCM of 20 and 80 times the HCF of 20 and 80. We just figured the HCF out to be 20. So then the LCM, these will cancel when I divide, and the LCM is just 80. So that's a quicker way if you have the same pair of positive integers. I'm trying to figure out the LCM and the HCF. Alright, so we covered irrational numbers, fundamental theorem of arithmetic or prime factorization, and then the LCM and HCF theorems and methods you need to know in order for NCERT. So I'm going to split this video into 2 parts, so we're going to finish off chapter 1 in the next video. I've put in the description below problems that you should be doing, because if you don't do the problems in the description, you're not going to, they might give Word a problem differently, and because here we just learned theory, right? So if someone asks you a problem with words and they disguise it as a problem with LCM and HCF, you're going to want to check out the problems in the description below. Yeah, that's all for today.